If you're tired of your answers to equations being too precise and accurate, then iteration may just be for you. Let's go. So we're actually going to look at two methods today, kind of linked together. The first one is called trial and improvement and has been on GCSE for ages. And the fun method of doing it is to use a table. So let's look at how that works with x squared equals 7. It's important to note this bit here, that we want to find our answer to one decimal place, so we want to end up with like 3.8 being our answer. And we're going to draw ourselves a little bit of a table. So our table is going to consist of x, and then x squared, and then a comment basically, so 2 question mark, which I will explain in a second. We'll get an x squared because that was the actual formula. So we'll try something out. Let's try 2. 2 squared is 4. But we don't want to get 4, we want to get 7. So 4 is too low. Okay, we're started. So that means we want to try something bigger. Let's try 2.5. The answer does talk about going to one decimal place, so this is fine. If we square 2.5, we get 6.25. That's still too low, but it's getting closer. Okay, what about 2.6? We go 6.76. If we square that, that's definitely getting closer, but again, still too low. So we'll try 2.7. That would give us 7.29, and that would be too high. Now, what does that tell us? That tells us that the answer is somewhere between 2.6 and 2.7, because when we squared 2.6, it was too small, and when we squared 2.7, it was too big. So we know we are looking for something bigger than 2.6 and smaller than 2.7. But which one does it round to? Does it round to 2.6? Does it round to 2.7? We actually have to do one last check here, which is the number 2.65, somewhere dead in the middle of our 2. We want to see if our answer is closer to 2.6 or closer to 2.7. If we square that, we get 7.0225, which is very, very, very close to 7, but is not 7. It's still slightly too high. So that means that our answer must be less than 2.65. So what does that tell us? That tells us that the real answer is somewhere here, and it's closer to 2.6 than it is to 2.7. So we can say that x is 2.6 to 1 decimal place. If we were asked to go to 2 decimal places, then we'd have to keep going and narrow it down to being between 2.64 and 2.65, and then look at 2.645. But fortunately, this question doesn't want us to do that. Okay, let's have a look at another example of this. Very similar sort of question. We've got x cubed this time. So we set up our table. We're going to have again x, and we're going to have in the middle here x cubed plus x, because that's what's in the actual equation. And then again, our little comment column, is it too big, too small? So we're going to start with 4 this time, and you're going to need to type in, this is very much a calculator topic, 4 cubed plus 4, which actually gives you 68. Not going to show the working for that because I've just typed it in. That is definitely too low. We want to get 100. And if you started with like 2 and you got an answer out of 10, you might want to bump up a lot quicker than that. Alright, we might try 5 next. 5 cubed plus 5, 130. That is too high, so we know the answer is somewhere between 4 and 5. But we want to go to one decimal place, so we need to get a bit more accurate still. Be sensible to try somewhere in the middle, so we'll try 4.5. If we put that in, we'll get 95.625. And make sure that you're getting these answers as well, that you're not just taking my word for it. You need to know how to type this in yourself after all. That's too low. We want 100. This is 95. So we need to try something bigger. So we'll try 4.6, and that's 101.936, and that is too high. So we have narrowed it down to being somewhere between 4.5 and 4.6. We know that the answer is bigger than 4.5 and less than 4.6. So again, we'll try that number in the middle, which this time is 4.55. And if we type all that in, we'll get 98.746. It kind of keeps going on, but the important thing is that it is smaller than 100. It is too low. So that means that the answer has to be bigger than 4.55. That means our answer is somewhere in this zone here. That means that x is closer to 4.6 to 1 decimal place. Now there is a really cheesy shortcut you can use instead of doing to be sure here, and that's to look at the last three things you wrote. I wrote low, high, high here. Which is the odd one out? It's the low. What value does that go with? 2.6. That's the answer. I wrote low, high, low here. Which is the odd one out? High. What does that go with? 4.6. That's the answer. So you can use that to check, but unfortunately you can't use that as your actual method. You do need to demonstrate why you're saying that. The marks are not just for the answer in this question, it's for showing the method of how you got that answer. And that last step of checking the 0.5 or the 0.05, that's very often forgotten. So that's trial and improvement. Now the great benefit of trial and improvement is you can use it on anything. You can use it on equations that we know how to solve, equations we don't know how to solve, equations that might not even have a solution, because it's just plugging numbers in and seeing how it works. So bearing that in mind, I'd like you to have a go at these two, and I'll give you a start point. So on the first one, shall we start with x equals 2? And on the second one, shall we start with x equals 3? Okay, pause the video now, have a go, and then unpause when you want to see what I've come up with. So 3, 2, 1. So there's my first three. I found that x is 2 gives me an answer too high, so I went down to 1, which is too low, so I went up to 1.5, which is too high, and let's do a few more steps. And we're pretty much at the answer there, so we can find it somewhere between 1.4 and 1.5, so we do need to do a little bit of a demonstration here, and the way that we check is obviously using the 1.45. The answer has got to be bigger than 1.4, but it's got to be smaller than the other two, so it's somewhere in this zone, so x is equal to 1.4 to 1 decimal place. Again, you could have used the odd one out method to check that. The odd one out is the 1.4, which is the only one that's low. Okay, same deal with the other one. We're going to start with x equals 3. This is 2 to the power of x, so the first thing you're going to type in is 2 to the power of 3. Best of luck. So there's my first 3. 2 cubed gave me 8, 2 to the 4 gave me 16, 2 to the 3.5 gives me 11.3 or something. It's a little bit too low, so I need to keep trying higher numbers than that. Let's keep going. So we've actually kind of gone the long way around here, but we do have to demonstrate the steps that we're taking. So it is important to show all of these values that you've tried. I think we're nearly there. That's almost 14. Phew, got there. Okay, so it's somewhere between 3.8 and 3.9 based on what we've said there. So 3.85 is the thing we have to use to check. So it's bigger than 3.8, it's smaller than 3.9, and 3.85 was too high, so it's also smaller than 3.85. So our answer is in this gap, and again we could use the odd one out and say it's 3.8. So x is 3.8 to 1 decimal place. Okay, so that's the general idea of iteration. Hope that went okay. Or the general idea of trial improvement. We're now going to expand on that a little bit. So iteration is basically asking, well, how do we come up with smarter ways of doing this? Because some of those tables took a little while to work through, particularly if you were looking to do 2 or 3 or 4 decimal places, it could take a very long time to do that. And one thing we can do is we can look at an equation we're trying to solve and we can rearrange it so it says x equals. So looking at this equation here, there's quite a few ways we could, well, there's 2 ways we could do that. We could subtract the x cubed and then divide by 3, or we could subtract the 3x and then we could take a cube root. Both of those should actually work, so I think it's worth talking about both of them. So first thing we could do is we could simply subtract the 3x from both sides, and then we could say, okay, well, if we cube root both sides, we have x equals the cube root of 7 minus 3x. And this is normally the stage, admittedly, in normal algebra, where you throw up your hands and go, oh god, this is impossible. But this is exactly what we want in iteration. It's a little niche. However, we could have done it the other way. We could have taken away the x cubed, and then we could have divided by 3. So these are both valid iteration formulas. And the idea of an iteration formula or an iterative formula is that it's something you can substitute an answer into itself, into itself, into itself over and over again until you get the actual answer to the equation you started with. So what do I actually mean by that? Well, let's look at the first one that we came up with here, the x equals the cube root of 7 minus 3x. What we're essentially going to do is we're going to put answers in here and we're going to get answers out here. So we're going to put a number into the right hand side and get an answer out on the left hand side. And let's actually start with x equals 2, like I think we did on the same question as on the previous page. If we use x equals 2, then we can say x is equal to the cube root of 7 minus 3 times 2. And if you type all that nonsense in, you get 1 out. In fact, I might need a little bit more room here. Okay, great. So what we do is we take that answer, x equals 1, and we substitute that into the formula again. So this time we'll do the cube root of 7 minus 3 times 1. If we do that, we get 1.587 ... kind of goes on forever. What this is doing is honing in on our final answer. If you remember from the previous page, the actual final answer is I think 1.4. We'll get quite close there. So let's use x equals 1.587 and substitute it into the formula. The cube root of 7 minus 3 times 1.587 ... is equal to 1.308, and so on. And you can keep putting these answers in, and we can keep getting answers out. So if we put 1.308 in, then the next thing we get out of there is 1.454, then the next thing we get out of there is 1.381, and they basically get closer and closer to that answer that we know that exists, which is about 1.4. If you keep running through this, you eventually end up with the actual answer. So that's the power of an iterative formula over this trial and error approach. It homes in on the actual answer. Now it can be a little bit confusing to write x equals 2, x equals 1. So what we tend to do instead is we tend to talk this as being our first guess was 0, so we call that x0 as like our starting point, or our first guess was 2, sorry. Then we got to 1, so we call that our x1 or our first guess. And then x2, our second guess, and then x3, and x4, and x5. And basically the language of iteration is to talk about these x1, x2, x3, x4, x5s. Would that have worked if we'd used the other iterative formula? Well, let's give it a go. So we could again start with 2, and if we put that into our other formula, that x is equal to 7 minus x cubed, so 7 minus 2 cubed over 3, we actually end up with minus 0.333 ... Okay, so that would tell us our first guess, our x1, is minus 0.333, and then we could plug that back into the formula and say we want to do 7 minus 0.33 cubed over 3, and if we do that, we'll get up to 2.345 ... And so our second guess is 2.345, and you'll actually find if you apply this one, and have a go at this yourself, that it kind of veers off into some weird places. We end up with this getting super big, and so that version of the formula won't actually work as an iterative. So there's a little bit of like discretion we've got to use here. Now luckily GCSE, they might ask you to show like how to rearrange a formula, but they're not going to ask you to pick one as an iteration. They're going to tell you the one that you need to use. But at A-level, they do like using that. So let's look at an actual GCSE question then. So here we've got a standard iteration question. Given x0 is 1, use the formula to find x1, 2, 3, and 4. So we want to find the first 4 guesses, essentially. And given that we're going to start using x equals 1. Now they phrase the formula a little bit differently to how we had on the previous page. They have this xn plus 1 and this xn. And all you need to think about that is that this is your input and this is your output. Your input is always just the n, and your n plus 1 is always your output. So we're going to put numbers into the right hand side of this equation, or we're going to put it into the more complicated side, is the slightly more savvy way of thinking about it. So let's start with x0 equals 1, and then if we want to find the next number, we want to find x1, we're going to need to do 8 minus 5 over 1 squared. So again, we're inputting it where that xn is. If we do that, we'll get an answer out of 3. That's great. So we can write down x1 equals 3. And then we want to find x2. So we do the same thing. We're going to go 8 minus 5 over 3 squared this time, because our x value is 3. If we do that, we get 7.444 dot dot dot. Okay, so x2 is equal to 7.444. And then we want to get x3 and x4. So we'll do x3 is equal to 8 minus 5 over 7.444 squared. And we'll get ourselves to 7.909. And you'll notice that these are getting closer, so they should hopefully be honing in on an answer. So we've got x3 is 7.909, and then x4 is the other one we want to find. So x4 is equal to 8 minus 5 over 7.909 squared, which gives us 7.92 or thereabouts. Let's say 920, so we're going to 3 decimal places as well. Now, the only thing that's missing from this question is they'd want to specify how many decimal places you give your answer to, but we're just sort of learning at this time. So here we've used an iterative formula, we've come up with an x1, 2, 3, and 4, and that's all there is to it. Okay, everything now is just repeating those steps. Make sure you know where the input's going, and you're good. So we've got a couple more exam questions on these last 3 slides. I'd like you to pause and have a go first, and then unpause when you want to have a go at seeing whether you're right or not. Okay? So unpause this one. I'm going to start in 3, 2, 1. First answer you should get is, I think it's actually 8/9, but I've put it as a decimal here, so 0.888. Second answer, quite close. You should get about 0.8108. I'm using the exact answer as what I input, so you might be off by like a single decimal place or something, but you should be around about there. And then my final answer, I've got 0.8296. So they might say, for example, that you should give your answer, say, rounded to 2 decimal places, in which case you go with 0.83 at the end of all this. But this question doesn't specify, so I think it just wants to see what you've worked out. Yeah, that's about all there is to it. Let's have a look at another one. So this is a bit of a 3-parter, and it kind of uses some of the trial and improvement stuff we looked at as well. So I just want to briefly talk about question A and B, and then set you C to look at yourself. So for A, it says to show that the equation has a solution between 0 and 1. Now how do we do that? Is we substitute in x equals 0, and we substitute in x equals 1. And we want to show that it's like too high, too low, so it must be in between the two, just like we did with trial by improvement. So if we sub in 0, we'll get 0 cubed plus 2 times 0, which is equal to 0, which is too low. And if we sub in 1, we'll get 1 cubed plus 2 times 1, which is equal to 3, which is too high. So it must be in between. That'll be enough. At A level you have to do lots more than that, but again, we're not there. B says to show it can be rearranged. So we talked about this rearranging before. There's like 2 ways you can obviously do a rearrangement. So you want to think about, well, am I getting rid of the cube? Is there a cube root in what I'm trying to show here? And there isn't. The cube is sort of maintained, so it's clear that I'm going to subtract that. So I'm first going to go subtract the x cubed across the other side, and then divide by 2. So a half minus x cubed over 2. And that's, all you need to do for that. And then finally C, which again, even if you can't do part A and B, you can still access part C. It gives us an iterative formula, and it says to use this twice. So we only need to find x1 and x2 to find an estimate for the solution of this equation. So I'm going to leave that to you now, and I'm going to unpause in 3, 2. So our first answer ends up being 0.5. Our second answer ends up being 0.4375, and that's done. That's our estimate for our solution. It says to do it twice, We did it twice. Okay, one more to have a look at. Very similar to the one we just looked at. I think you should be able to try the whole thing yourself now. Unpause when you're ready. I'm going to go in 3, 2. So there we go. If you sub in 1.5, you get a negative number. If you sub in 2, you get a positive number. And as this is equal to 0, according to our formula, obviously our x must be between those two numbers. 1.5 was too small, 2 was too big. It's in between the two. Okay. Part B, again, unpause when you're ready to have a look at it. Your first answer is going to be 1.630. We're doing this 3 times, so we want to get all the way to x3. Your second answer should round to about 1.637. We need to do one more though. And there we go. There's our estimate. Okay, so that's the general idea of iteration. Yeah, inequalities next, I think.